Welcome back, friends. In the last class, we talked about how we can draw the distance time graph and velocity time graph from the real life situation. We were given that, let's say, if a person who's standing here, he moves in the forward direction and then he stops at place A, then he still moves, he keeps moving and then reaches to place B, spends some time, then he comes back. How can we draw the velocity time graph and distance time graph? That's what we've learned in the last lecture. Now in today's class, what we're gonna do is we're gonna learn about how to read the distance time graph and the velocity time graphs. Distance time graph and velocity time graph, that's what we're gonna do. So I'm gonna first of all start with the distance time graphs. So if this is the distance time graph given to me, the distance time graph looks something like this. And in this one, if I extend this from here, it stops here and then it continues moving in the downward direction, then somewhere here, and then ends somewhere here. I wanted to find if this is the distance time graph given to me, and let's say this is 5 meters. I'm just taking some random values, and this is 5 seconds, and then this reaches to 10 seconds here, and this reaches to 15 seconds, then this I will take it as 20 seconds. This is not up to the scale, so kindly pardon me for that. So 25, this is 30. We're just taking some random values to understand the distance time graph. That's what we are doing because our objective is to learn the graph. So now I wanted to find what is the net displacement of the person. So in this case, when you are reading the displacement time graph and you wanted to find the net displacement, you will see where that graph ends. This graph ends at this point. So what is the displacement at this point? Although the time consumed is 30 seconds, but I'll look at the displacement on the y-axis. So displacement here starting from 0, and this is in east direction. So displacement here is 0. So the net displacement, because you end up at the initial point, so the net displacement will come out to be 0 because you started from 0 and you end up being at 0. So that's why the net displacement is 0. Now how can I read this graph is, first of all, I covered 5 meters. I covered 5 meters in 5 seconds. 5 meters in 5 seconds in east direction. And then this, what does this horizontal line shows on the displacement time graph? That it means I am not moving anywhere. So it means the displacement here is 0 for this section. Let's say this is A, this is B, this is C, this is D, this is E, and this is F. For section B, the displacement is, for section B, displacement is 0 because see here, displacement was 5 at this point, and this point also at this location the displacement is still the 5 meters. Then if it is a negative slope, if it is moving like this, for section C, what's happening for section C? It means, so I'm gonna draw a picture. This car is moving in the east direction for part A. First of all, for part A, the car moved in the east direction, covered 5 meters in 5 seconds, and then car stopped here. This was my reference point. This is my reference point from where the car started. And then for section C, the car started moving in the opposite direction, and it kept on moving. It reached here, but it didn't stop here. It kept on moving for next 10 seconds. So C and D, I'll combine them together. So this is 5 seconds and this is also 5 seconds. So it kept moving for next 10 seconds and it reached somewhere in the west direction with respect to the original point. This is the original point. From here it reached to the somewhere in the west direction. Let's say this is 5 meters in the west direction, and then the car stopped here for 5 seconds, and then car moved backwards and reached to the final position. That's how we can interpret the displacement time graph. Now we're gonna try and look for the second graph. So velocity time graph. Now velocity time graph is little tricky compared to displacement time graph. If this is the velocity time graph drawn like this, and again velocity east in this direction, and and then it comes down here, and then yeah, let's first of all look for this one. So what's happening in this one? If this is the velocity time graph, if let's say we are asked to find the displacement by reading the velocity time graph, and this is, again, I'm gonna take a simple number, 5 meters per second. Velocity is always in meters per second, so that's why I'm taking 5 meters per second, and the time here is let's say 10 seconds, and then this 20, and then here 25. So I wanted to find the net displacement. Find net displacement using velocity time graph. So to find the net displacement by using the velocity time graph, we will always look for the area under the curve in this graph. So what is the area under the curve? This is the total area under the curve. Now it's very hard to find the area for this shape, so I can convert it into three different shapes, or three different segments, shall I say. One is this segment, this becomes a triangle, this triangle, and then this becomes this becomes what? A rectangle, and then after this becomes another triangle. So if I find the area of all these triangles and add those areas, that's going to give me the net displacement. So let's look into what is the net displacement in this case. So area of the first triangle, area of a triangle, first of all I'll tell you, half times base times height. That is the area of the triangle. Formula is, so half times base value is 10 seconds, from here to here it is 10 seconds, 10 times height becomes, this is the height, so from here to here this is 5 seconds, 5 meters per second. So this value will come out to be 25 meters. 25 meters, yeah, because if I look into the units, if this is seconds, this has a units of second, times 5 has a units of meters per second. Second and second cancels out, the final unit will be meters. So we found out the area for the first section, that comes out to be 25 meters, and area of the second section, this section is 10, and this section from here to here is 5. So area A2, I'm gonna erase this, I'm gonna make some space here, I'm gonna call it as A2. So A2 will be equal to 10 times this is 5, so that will come out to be 50 meters, A2. And then A3 will be equal to how much? If I look into A3, this I'm gonna name it as A3. So A3 comes out to be, again, this will be 5, and then this will be 5. So 5 times 5, this is a triangle, so half times 5 times 5, this comes out to be 12.5. So total area which is equal to the net displacement, total area is equal to 25 plus 50 plus 12.5, which comes out to be, I think this will come out to be 87.5 meters. That's the net displacement. Now if I wanted to understand what's happening in the real life scenario in this case, so I'm gonna erase this, I'm gonna go to the next slide rather than erasing this. Oops, yeah. So it looked like this, went up, then like this, then like this. Now this was 5 meters per second, and then this was 10 seconds, this was again 5, and then this was 20, and this was 25. That was the graph. So first of all, and this was in the east direction, so you started moving in the east direction first of all. So here is your car, the car is moving in the east direction. It is moving at 5 meters per second, and then it started from 0. The velocity here, the velocity is 0. It's not sorry, I apologize for my words. It didn't start from 0, it reached to the 5 meters per second. It started from, the car started from 0 meters per second, and reached to the velocity of 5 meters per second in the east direction. That's what it is. Over a period of 10 seconds. So the velocity increased, and then did it stop? It is a horizontal line. No, because it's a velocity time graph, so I can't say that the car stopped. What happened in a real life scenario? The car kept on moving. This was 5 meters per second. Car kept on moving at 5 meters per second speed or velocity in the east direction for next how much? 10 seconds. And then what happened? Did it change the direction? It's moving in the downward direction. I would like you to pause the video and try and think about it. So the answer is it did not change the direction. It's still moving in the east direction. But it slowed down, and in the end it came to the rest after 5 seconds. It's still in the east direction but slowing down, applying the brakes. So in this case, the car accelerated in the forward direction, then kept moving at the constant velocity, then slowed down, applied the brakes for the third section. That's what happened for the real life scenario. I'm going to take one last problem and I'm going to finish this lecture. So if it is like this, this is the velocity time graph, and this is again east direction, and this is the west direction. So how to read this graph? What's happening? What's happening here? The car is in the west direction. So if this is the origin point, the car is somewhere here in the west direction. Okay, car is moving in the west direction. So this is the car which is moving in the west direction, and the car keeps on moving in the west direction. But what's happening? See here, if let's say this is 5 meters per second in the west direction, it's with the period of time it's slowing down, it's coming down to 0. Over a period of time, car will come down to a velocity of 0 meters per second. Then in the next second it will take turn and start moving in the other direction, in the east direction. So it's making a little hodgepodge. So it started moving in the east direction. This is the direction in which car will move. So where did the car change its direction? Car changed its direction at this point. So this 0 velocity means car changed its direction at that time. Let's say this is 10 seconds. So if I ask you a question, at what time the car changed its direction? At 10 seconds, the car changed its direction. From the west, it was moving in west, then it changed to east direction. So hopefully you were able to understand how to read the velocity time graph and displacement time graph. I'll see you with another video. Bye now.